Hi, I'm going to start with kind of a full analysis of one of the parts of problem 7 from our last online assignment. It was to pick 4 letters. This was 7b actually, if you want to pick 4 letters out of the set called the cryptographer's alphabet. So A through F. And then sort them, and put them in order. And I don't mean the words, I mean the letters in the word. I think it was made clear in the assignment. And how many ways were there to do this? Well, what you could do was think about how many choices you had for picking 4 letters in any order, and then divide by how many ways you can reorder things. So we got that there would be 4 choices, 6 choices for the first one, then 5 for the second, then 4 for the third, then 3 for the last. And then we would have to divide that by how many ways to reorder them after we done them, which is a factorial, 4 times 3 times 2 times 1. Or straight up, you might know this is the choice function. This is 6 choose 4. Which is what, 20, I think? No, 15. Because, let's see, 4, 3, and 4, 3 cancel, and it's 30 over 2. Yeah, 15. Okay, so let's actually use a choice tree to draw all 15 of these things, or locate them. It's actually not horrific. I mean, 15 is kind of a big number, but it's not that bad to organize it. I want to give you an example of that. So, I guess the first thing to ask is, how many choices are there for the first letter? So your first letter, well, it could be an A, it could be a B, C. What are all the possibilities? If I do a C, I think I can still do a C in this alphabet, but think about what's left for the second, third, and fourth letter in this thing. It would just be D, E, and F. So if you started with a C, you're going to have D, E, and F. Right? Your choices are limited. But it's certainly the case that you can't have the first letter be D. Why? Because it's supposed to be the earliest one in the alphabetically in the most of 4 of them, and there's only 3 more. So no, that's out. So we've got it, A, B, C. That's our choices for the first letter. All right, so I'm going to take A up there and leave a lot of room for B, or for A rather, and very little room for B and C. Actually kind of just went through why I don't need to leave a whole lot of room for C. It's because the only possible word we get then is to choose D, followed by E, followed by F. Right? There's just, if the first letter is C, the other 3 have to be D, E, and F. If the first letter is B, we've got some choices. We can let the second letter be, what's the possibilities? Well, I guess it's either C or D. But like before, if this is now the second letter is D, what choices are there for the third and fourth letter? It can only be E and F. With C as the second letter, there's still some choices, right? We could go to either D or E. E forces F for the last one. D, well, could be E or F. So you can read through the branches of this tree. What are all the selections? The very last one we would probably list would be C, D, E, F. In fact, I think these are coming kind of in order, aren't they? B, C, D, E, B, C, E, F, B, D, E, F. You know, there's a natural ordering to these outcomes. All right. What about if our first letter was an A, because there's more choices, more options, right? The next letter could be B, or it could be C, or it could be D. But if it's D, there's not much options after that. You have to have E or F. E and F, excuse me, is the next things. This is similar, I mean, actually, I think we're going to see sort of a copy of the part of the long end of the branches down there occurring up here. Because if your second letter is D, in any place where your second letter is D, your choices are limited to E, F after that. And any place where your second letter is C, you're going to see this little sub-tree, sub-branch. D and E are the next choices, and then E, F, and F on the end. Okay, so we can sort of copy this piece of tree into here. That one just goes to F, and D can go to either E or F for the fourth letter. Awesome. But we haven't done a B before. So we have to think about what are our options if our second letter is B. Well, our third letter could be C, or it could be D, or couldn't it be E also? And that's the one where you sort of have limited your choices. If your third letter is E, your fourth letter just has to be F. Any place where you see an E in position 3, the only thing that can follow it is an F. So that's fine. What is the things that follow on after a D in position 3? It branches to either E or F. And where can we find any C's that have occurred so far not in position 3, they haven't. So we got to figure out what goes on from a C. Oh yeah, but it's not that hard because we're at C and the only options are D, E, or F. There's a three-way branching there. And we're done because that's the fourth letter, right? So did I in fact get 15 things? I'm just curious. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So yeah, we just brute force showed that 6 choose 4 is in fact 15. These words that are coming in sorted order correspond to sets. Whenever you have a set, I would like to, for computer science people, to think of it this way. If you wanted a data structure that encapsulated what a set is, you know it's supposed to be an unordered collection. So what you would do with an unordered collection is sort it. So that way you know if you're seeing the things in order, it's a set. A set is best contained as a data structure in a sorted list of elements. I'm going to do something which may seem to be completely different now, but in fact it's not. This is quite well related. But I want to look at multiplying polynomials. The classic example, the classic things people know about how to multiply polynomials is when the two things are what are known as binomials. They have two terms in them, and I'm just going to generically call them x and y. So the sort of simplest example of multiplying polynomials, it's not totally trivial, is x plus y times x plus y. If you have a monomial times a binomial, that's really just distributing. And if you have two monomials, that's just really just multiplying, adding the exponents together and blah, blah. So this is a sort of smallest interesting case. And everybody knows this from the FOIL rule, I think. It's going to be first times first is x squared. You get an xy and an xy from inner and outer terms, so that's 2xy's. And then y squared, last times last. So don't, from here on, we're going to stop using FOIL. This first, outer, inner, last. thing. It's great for this, but it works only in this scenario where you've got a length 2 thing times a length 2 thing. I'm going to show you the same exact product in what's called the table method. So here we just foiled, here I'll show you a table. The table method is you put the terms of each polynomial in either the column or the row headings of a table. And then to put an entry in this table, you multiply the column and the row headings. So you get an x squared right there. X times y, xy goes here. I should call this yx, but since xy and yx are the same, I'm going to write it as xy. And then we get y squared down here. And so this seems like more work than the FOIL method, right? But this can be done whenever you have any pair of polynomials. So it does end up being less work. Essentially, it's a systematic way to organize things so that you multiply everything in this one times everything in that one. We're getting all the possible cross products. There is one last step to do, which is to combine like terms if there are any. And by the way, notice how they appear like on a diagonal. So you get x squared plus 2xy plus y squared, just like you did in the other method. Where the table method shines, though, is when you get past just 2 by 2 tables. So let's figure out what x plus y to the third power is, just as an example, because we've already figured out what x plus y squared is. So this is x plus y times x plus y squared, which was x squared plus 2xy plus y squared. So let's set up a table for this. X squared, 2xy, and y squared, those are the column headings, and then x and y are the row headings. So super long tail on that y. Okay, so multiplying by x isn't hard. It just bumps up the exponent on any x's that are in there. So you get x cubed in that spot. 2x squared y here. And there is no x in that one, so we just get x times y squared. And then multiplying by y, it's similar. We get y times x squared. 2x and then y squared. And finally y cubed. And notice, like before, the like terms are happening on kind of diagonals through here. Xy squared with a 2 on it, xy squared with a missing thing, but a 1 on that. So those two add up to 3, xy squared. These two are both, I wrote this one in the wrong order, but still it's x squared y. So we've got 3x squared y. So when we combine any like terms, we get x cubed, 3x squared y, and 3xy squared, and then finally y cubed. Now, you may see where this is going, right? This is the form we've used before to multiply out things, and we got the coefficients, you recall, out of Pascal's triangle. But Pascal's triangle isn't magic or anything. Pascal discovered it more than likely by doing what we just did, multiplying out polynomials. And you notice how the coefficients in here were 1, 2, and 1, 1, 2, and 1, and then we did this diagonal shift where the like things are. That makes sense that this 3 is a 2 plus a 1. That's a reflection of the way you're adding the terms on either side of you on the row above to get a term in Pascal's triangle. Well, that's where we're going, right? We want to actually see how Pascal's triangle gets generated. And this table method is a great way to do that. I guess to get one more data point, I want to see what x plus y to the fourth power is. I'm going to do x plus y to the fourth power 2 different ways, actually. One of them is x plus y squared times x plus y squared. The other option would have been to do x plus y to the first power times x plus y cubed. And this way is actually kind of better in terms of where we're heading, but I think just to show you an example of the table method, It's a little more meaty. Let's do x plus y squared. So that's x plus y squared times x plus y squared. You have to remember what x plus y squared was. Normally when I'm doing the table method, I don't write the pluses in between the things. I just leave space. X squared, 2xy, y squared. Those are the terms of, well, it's the same thing for rows and columns. And then you can multiply column heading times row heading, and you get x to the fourth in there. I'm going to jump to the end. You'll get y to the fourth down there. What else are we going to get? Like, there's some easier terms. X squared, y squared here. And x squared, y squared here. I guess I better start getting systematic. What's going to go right there in the middle of the first row? It's x squared times 2xy, so it's 2x cubed y. And then let's fill out that row. We're all empty there. Let's see. We got a 2, an x cubed, and a y. You see the like terms? In the middle of this thing, we're going to get 2 times x times y. Yeah, it's 4x squared, y squared. And last in that row is 2xy cubed. What's left down here? 2xy cubed. So if you combine the like terms, and again, notice that they're on these diagonals through here. I'll try to indicate them. There's one. So let's start with x to the fourth, then there's 4x cubed y. Then there is 6x squared y squared. Everybody see that one? It's 1 plus 4 plus 1 of them. Then there's 4xy cubed. And lastly, y to the fourth. And you should recognize the 1, 4, 6, 4, 1 that are the coefficients there coming out of the fourth row of Pascal's triangle. Let me do this another way, which would be to multiply x plus y times the cube of x plus y. That's x cubed, 3x squared y, 3xy squared, and y cubed. This route is sort of better in terms of seeing how Pascal's formula comes about. X times x cubed is x to the fourth. This middle, or not middle, there is no middle, it's an even length cable. But this term is going to be 3x squared y times another x, that makes it 3x cubed y. Here we get 3x squared y squared. And finally, xy cubed. Right here, it's x cubed y, 3x squared y squared, 3xy squared. I lied, 3xy cubed. And finally, y to the fourth. Similar to before, you see these diagonals where the like terms are. And let's just, I don't think I need to write it a second time. X to the fourth is the first thing. 3 plus 1 is 4x cubed y. 3 and 3 is 6, x squared y squared. 3 and 1 is 4xy cubed, and finally a single y to the fourth. Yeah. So what we're noticing in here is that if you look at if you're looking for the fourth row, you just need to take the third row and sort of think about shifts of it and add corresponding terms. That amounts to the same thing as what we normally do with adding the numbers on either side of this in the row above. So that rule for generating the next row in Pascal's triangle has a name. It's actually called Pascal's formula. And it says that n plus 1 choose k is equal to n choose k plus n choose, I hope I'm doing this right, is it k plus 1? Nope, it's k minus 1. Yeah, that makes sense. Okay, so the kth one is the sum of the kth one from the row above plus the one before that from the row above. And that's Pascal's formula. Can we try to argue why this is really the case? I mean, we just sort of observed it, right, in the table of powers of x plus y, and it seemed to be the right thing to do, but we actually have a formula for these things, right? And like n choose k is, well, it's the top factorial, so n plus 1 factorial would be what's on the left there, divided by two things, the bottom number factorial, and also the difference between the two things. What's n plus 1 minus k? Well, I guess I'll write it this way, n minus k plus 1. So my question to you is this true, that if I just plug these guys into the rule for building one of these binomial coefficients, with the formula in terms of factorials, does it all work out? So we have, for that first one, n over k, it's n factorial, k factorial, and then n minus k factorial. And the second one, well, the top is still n factorial. The bottom is k minus 1 factorial. And what else? N minus that number factorial. N minus k minus 1. I feel like I want some scrap paper to work on. N minus k minus 1. Oh yeah, that's n minus k plus 1, which we've seen before, right? So is this, well, I forgot the plus sign in between, is this sum of all these factorial things even possible? Turns out, yeah. It's a little tough, but we just want to get a common denominator for these things. And they're mostly common. Like that k factorial has k down all the way down to 1, and this guy has k minus 1 all the way down to 1. These guys only differ in the sense of, well, this one could use an extra k, and then they'd be the same. Similarly, these two things are almost the same number factorial. This one's 1 bigger. So it's got 1 extra term than that one does. All right, so this is a sort of a poor practice on my part. I shouldn't write, an equal sign and then put a question mark on it. Let's start with what's on the right and see if we can work with it and get the thing that I just erased. That's what we're really trying to do, is make a little proof here. So the idea is to multiply top and bottom in these two fractions in such a way that we end up with the same denominator. That denominator is going to be k factorial and n minus k plus 1 factorial. So what did I multiply top and bottom by on this first fraction? I haven't done it in the top yet, but what I need is that one more term, n minus k plus 1. And in the second fraction, how did I change that to get this denominator? Well, I guess I better put down that denominator first. K factorial, n minus k plus 1 factorial. The n minus k plus 1 factorial was already there. What I had before was a k minus 1 factorial. I must have multiplied by k to create that. So in the top we have n factorial times k. So now, great, we can put them over the same denominator. We have put them over the same denominator, but now I'm saying we can write them as a single fraction with that denominator down here. Whoops, gotta keep that factorial sign. What's in the top? Notice that both of them have an n factorial in them. So we could factor that out. And then what's left, n minus k plus 1 and a k. N minus k plus 1 plus another k. That k cancels with this minus k. We just end up with n plus 1 there. Now, what was I supposed to get? I was supposed, well, actually, remember, I was supposed to get n plus 1 factorial. Look what we've got. The numerator is right. The denominator is supposed to be, well, there's supposed to be a k factorial, which we've got. And the other thing there's supposed to be is the top number minus the bottom number. Factorialized. But that's exactly what we've got. N minus k plus 1, same thing, factorial. Woohoo! So we've proved Pascal's formula, which is kind of cool, but there's another approach we can take, and that's actually neat, right? When you've got a proof, but you've got an entirely different way to do it, you're really certain of the result if you get that sort of situation where the same thing can be proved multiple ways. So the other approach is entirely about sets. So you see, n choose k is equal to the number of subsets of a set of size k. Oh, sorry, I just said it wrong. The number of subsets of size k from a set of size n, from the top number. Let me just write it as 1, 2, up to n. Right? That's just another approach to what this is. The sets are unordered collections. They're of size k. This is a selection of k things, but unordered. That's where we got our counting formula. So n plus 1 choose k. That's same thing. It's all the sets of size k that you can take from 1 through n plus 1. And what we're going to do is use the addition principle to count these things. See, there's two options for a set taken from 1 through n plus 1. I can pick any particular thing, but since n plus 1 is something I know for sure is in there, let's pick that. A subset of size k either contains that thing or it doesn't. So that says that n plus 1 choose k should be equal to the number of subsets containing n plus 1 plus the ones that don't contain n plus 1. Right? There's two options for a subset. It's either got n plus 1 in it, fine, or it doesn't, fine. Well, how many of each of these are there? Let's think about that. The number of subsets containing n plus 1, these are supposed to be sets of size k. Well, that means you've got n plus 1 plus k minus 1 other things. And those other things are taken from 1 up to n. In other words, this collection, number of sets that contain that, is n choose k minus 1. What about the ones over here? Well, if you don't contain n plus 1, then you've got to get all k of the things out of the set, out of the numbers from 1 up to n, just 1 through n. You're not going to use the n plus 1. And that is n choose k. Completely different way to get at it. But, because of what these things count, you know that n plus 1 choose k is n choose k minus 1 plus n choose k. One thing we should finally mention is that these n choose k things are an array. We see it as a triangle, but it's actually can be thought of as a square thing too. I'm writing it out as a giant table. You could actually, you could code something up to do this. You could put this into a spreadsheet and actually get the thing to produce the binomial coefficients. In this version of things, you should just honestly kind of mime this a little bit. You take the Pascal's triangle and just shift it over like that. Right? So, well, anyway, n equals 0, k equals 0, 1, 0 choose 0 is 1 by definition. What do you think about 0 choose 0? It's got 0 factorial over 0 factorial and 0 minus 0 factorial. And all of those numbers are 1s, so you do in fact get 1. Okay. The first row of Pascal's triangle we know has a pair of 1s in it, but because of this shifting I've been talking about, you end up seeing them like that. What do you do with this entry? That would be 0 choose 1. What should that be? Well, let's try to write it in terms of factorials. It has 0 factorial in the top and 1 factorial in the bottom and 0 minus 1 factorial in the bottom too. Huh. Really, this is undefined. I mean, I don't know what to make of all the numbers from -1 down to 1 multiplied together. Feels like it should be undefined, but it could also just be thought of as an empty product, and so that would be a 1. So again, we'd have 1s over 1s. But there's another way to say this. Think about it in terms of sets. The n here is the set from which we're choosing things, and the k is the size of the sets that we're going to be choosing. So how many ways can I pick one thing out of a set that doesn't have any things in it? That sounds more like it's impossible. There's no way to do that. So in fact, the entire row after the first one, the entire 0th row, is 1 followed by zeros. And similar arguing says after the couple initial 1s, this whole row is zeros. I mean, think about what, like for instance, that 0 says. We've got a set of size 1. How many ways can we pick 4 things out of 1? You can't do that, so 0. All right, so the next row of Pascal's triangle is 1, 2, 1, and then we've got zeros after that. 2 also. You should notice something that is happening here. We seem to be getting a diagonal stripe of 1s. And that's quite reasonable, because these are numbers where the n and the k are the same. That's where the diagonal positions are. So you could say that's n choose n. Think about what n choose n should be if we use the factorial notation. You'll have n factorial in the top, and you'll have n factorial in the bottom, and the difference between n minus n, that's 0 factorial, also in the bottom. 1 and a thing over itself. So that's 1. Great, so we know there's this stripe of 1s. And then the rest of the table is pretty easy to fill in. Let's just see what what's Pascal's formula, the Pascal recursion says in this situation. Where I'm getting a number, like if I want to know what to fill in that position right there, I look above me and above me to the left. That is, think of this as a little template. Take those two things, add them up, and put it down below. And Well, what would I do right here? My template would sort of be off the edge of the table. I don't mean that it would include that too, but that there's nothing to add there. So that means we should just get ones forever in the first column. That's another one that we can sort of work out. Those are things where, from whatever n is, we're choosing zero things. That is, it's something in the form n choose 0, which is n factorial over 0 factorial. And what's the difference between n and 0? N factorial. In fact, it's the same calculation as n choose n, isn't it? These guys are equal to each other. The far ends of the table are the same. You always get ones. All right, so do we need to talk more about this? This is a 3 and a 3, and this is 4, 6, 4. I kind of like the squared up version of Pascal's triangle because it helps you understand a few other things. Where I'm supposed to be heading is a thing called the binomial theorem. And this is just expressing that trick that we've talked about of how to multiply out a binomial's power using binomial coefficients. In fact, that's why they're called binomial coefficients. Oops, I didn't finish the word. Binomial theorem. So yeah, it tells us that we can write x plus y to the nth power as a sum. And let me give you the pieces of this sum separately. One thing is there's going to be a binomial coefficient, and choose k. And that k actually is the index for our sum. So we're going to run k from 0 all the way up to n. And choose k. The other piece that you're going to see is a power on x and a power on y. And traditionally, we write this with the k being the power on y. And the power on x is n minus k. The two of those numbers add up to n, which if you've done this a few times, you'll see that. The power on x and the power on y always add up to the total. Great. So that's the binomial theorem. Can we prove this directly? Yes, we can. The proof here would best be done by induction. So let's look at the base case. What is the smallest value of n that makes sense? Actually, I didn't quantify it. I'm a bad person. I should have said for all n in the naturals. Now what's the smallest n that makes sense? Yes, n equals 0. Okay, so x plus y to the 0 power, unless x and y happen to add up to 0, then you've got an indeterminate form, but assuming that you're not looking at something silly like that, anything to the 0 power is 1. I have thrown an assumption at us there, but that's okay. I think we can live with it. What's on the right-hand side? What has that sigma got in it in the base case? I usually like to spell out what I'm talking about. N equals 0. Well, let's just say it. Right? It's the sum for k equals 0 to 0 of n choose k. X to the n minus k. Well, wait a minute. Oh, yeah, I guess I got it right. N minus k, y to the k. Well, what is this? This k is equal to 0, and so we've got exactly one term in this sum. And that term is n choose 0. There's one way to get 0 things out of a set of size n. Don't pick any of them. What's the power on x? N is 0. So 0 minus k. But k is also 0. K, the only term in the sum is when n is 0 and k is 0. So we get x to the 0, 0 minus 0, and y to the 0. Yeah, this whole thing is just 1. Unless x and y is either x or y, or both of them are zeros, then you might have an indeterminate form. Yeah, so the base case is looking solid. Let's see how the inductive step will look. What shall we use for our induction variable? I've already got k in use for the index on the sum, so I don't want to use k. How about m? So for our inductive step, suppose m is some number bigger than 0, some natural number bigger than 0. I feel like that's a very weird way to write it. I don't think people normally write it that way. Let me try again. Suppose m is a natural number and m is greater than 0. And if I take the sum from k equals 0 to m of m choose k, x to the m minus k, y to the k, that will be equal to x plus y to the k, x plus y to the m. That's our inductive hypothesis, that basically the formula we're writing down for the powers of x plus y works if you're at stage n. Well then, x plus y to the m plus 1, because that's what we need to do, right, so that that next domino falls, is equal to x plus y times m. I just said that funny. I said that wrong. It's x plus y times x plus y to the m. And, well, that one is our inductive hypothesis. Right? So this is equal to x plus y times a sum that has, let's all write it up, but it's k from 0 to m. K 0 to m, m choose k, x to the m minus k, y to the k. Not so horrible. You can just distribute. See, this is one big sum, and there's a sum with 2 terms in it there. So this looks like x times that sum plus y times that sum. I mean, well, no, I was going to just abbreviate it to sigma, but we should keep the details here. K's go from 0 to m choose k, x to the m minus k, y to the k. And then there'll be another term. Here I have to abbreviate because it's going to run off the end. Okay, but it would be y times, again, the sum we have written right up here. Well, what comes next? X to the m minus k, y to the k. I'm not going to write them. I don't want to write on my landlord's wall. I would do this at school, but not here. All right. Well, this is not too bad. We can go ahead and multiply x into that sum, and we can go ahead and multiply y into that sum. Because what is multiplying a sum by x going to do? Basically, it's just going to lift all the powers of x by 1. So what I've got there is a sum that goes from 0 to m. It has m choose k in it. The power on x, however, is m minus k plus 1. Power on y is unchanged. I'm writing a little bit big, and I'm going to have to squinch up to try to fit it in here. Now the next sum is one that goes from 0 to m choose k, x, well the x power is unaffected because we multiplied by y down in here, so that would be x to the m minus k. Y, however, is going to be to the k plus first power. So what I want to do is actually think about how to combine these two sums into one. And the problem here is that the powers on, say, y, which used to be the thing that sort of told you where you were in the sum, have been shifted in this one. So if I want the index to appear right there, what do I got to do? I've got to add 1 to the index. So let's sort of re-index this sum. Instead of going from 0 to m, let's go to the powers that go through the powers that appear in this. When k is 0, this is a 1. When k is m, this is an m plus 1. So that is, I want to re-index that second sum. This first one, leave it alone. 0 to m choose k, x to the m minus k plus 1, and y to the k. But the other one, I'm going to change the variable, and I'm going to have it be a sum j equals 1 to m plus 1. How did I work this? If that number, the power on y, is to be our new index, then j is equal to k plus 1. Can we just scribble that down somewhere? J equals k plus 1. What does that mean k is? J minus 1, right? So this could be written as m choose j minus 1. M minus k, but again, k is j minus 1. That's m minus j minus 1. The power on x is x. No, it isn't. It's m minus k plus 1. Oh, it's the same as the power on x over here. Okay, now I messed that up twice, so I just want to double check what I've done. K is j minus 1. M minus j minus 1 is m minus j plus 1. Yeah, okay. And then finally, that's y to the j. Now these two sigma notations were difficult to come by, but they're maybe some people might prefer to write this out in expanded form, but I'm trying to give us practice thinking about sigma notations, so we'll stick with that. But notice that this sum, the variable goes from 0 to m, and in this sum it goes from 1 to m plus 1. Now that I've done all that work, I wanted you to think about k switching to j, but honestly, why not just call it k again? That is, you could have made the substitution k is replaced with k minus 1. I'm gonna undo this. I'm gonna change my variable back to k. That's not really undoing the substitution. But the other thing I'm going to notice is this one runs from 0 to m. This one runs from 1 to m plus 1. They have an overlap, but they're not the same. You should write this as two pieces. The the initial term in this case, and then overlapping part that runs from 1 to m, what would that initial term be? It's when k is 0. So we have m choose 0, x to the, well, okay, whatever. Y I know is y to the 0, x to the m minus 0 plus 1. I think that's m plus 1. M minus 0 plus 1. Okay. Okay, and then the rest of the sum is everything from k equals 1 to m. Choose k, x to the m minus k plus 1, y to the k. Now let's also write down the second sum, but we're going to do it in a similar way. We'll write the overlap between these two sums where we go from 1 to m and then an additional term. And now I'm gonna go back to calling the variable k. K is going from 1 to m. M choose k minus 1. X to the, what's the power? M minus k plus 1. And y to the k. And then that last term, the m plus first term, okay, we can, I was staring at that for a second because I was like, wait, the thing in the bottom is going to come out bigger, but it's not. It's m choose m plus 1 minus 1. It's m choose m. And then x to the m. Okay, so this additional term here, whoops, I'm not writing it there, but writing it down here, is got x to the 0 power and y to the index power. The index was the m plus first, right? We're getting that last term. So this is kind of a neat way to write it out because what this says is overall x plus y to the m, x plus y to the m plus 1 has a first term that's got a 1 and x to the m plus 1. And it's got a last term that's got a 1 and a y to the m plus 1. And then in the middle, do you notice how both of these sums now overlap? The variable goes from 1 to m in both of them. The power on x is m minus k plus 1 in both of them. The power on y is k in both of them. So we can combine them into a single sum. It's brilliant that they're just lined up perfectly for us to do that. So I'm just going to leave what's on the bottom in place and say what that's equal to up high on the board. Here we've got x to the m plus 1. In the middle, we've got a sum that goes from 1 to m of the sum of, I'm going to write it as two things, m choose k plus m choose k minus 1 and then the corresponding powers of x and the corresponding powers of y. Whoops. No, let's keep x first. X to the m minus k plus 1, y to the k. And then there's one more term, which is a y to the m plus 1 from this. Cool. Now, notice that this x to the m plus 1 is exactly what we get out of that formula if k is equal to 0. So think about what the k equals 0 stage says. Wait, before I do that simplification, let's use Pascal's formula. This thing that I put in square brackets, that's m plus 1 choose k. powers on x and y are what they are here before, m minus k plus 1 and y to the k. And then we still have that y to the m plus 1 on the tail. So right, this is the sum in the middle. It starts with x to the m plus 1 and it ends with y to the m plus 1. Now what I finally want to do is recombine these into a single sum. This is crazy, but it works because that guy is the 0th term of our sum, and this guy is the n plus first term of our sum. So think about what k equals 0 says in that sum. You've got m plus 1 choose 0, x to the m minus 0, that's just x to the m plus 1, and y to the 0. That's 1, and that's 1, and that's x to the m plus 1. See that this whole thing here is that. And if you work out the k equals m plus 1 version of the sum, then the binomial coefficient is m plus 1 choose m plus 1. The power on x, oh, this is the one that stumped me before, so I remember it. That's x to the 0. And the power on y is m plus 1. Well, a number choose itself is 1. That's 1. Yeah, this is y to the m plus 1. So this whole piece here is that. So in other words, we can just change the limits of the sum. The 0th term is the thing I pulled out on the left. The m plus first term is the one I pulled out on the right. I hate to have to do this, but here it goes. Well, I guess I'll erase this. Think of this stuff what I just did as scrap work. So yes, we can do this as a single sum where the index variable starts at 0 and goes to m plus 1. It's m plus 1 choose k, x to the, let me write this slightly differently. It's m plus 1 minus k. And y to the k. And that, finally, is where we want it to be, because this is indeed the m plus first version of our sum. We finally connected the dots from x plus y to the m plus 1 to the sum formula with all the n's replaced with m plus 1's. That's our ticket to know we have finished our induction proof. We reached the right-hand side of the m plus first version of our statement. So I'm going to end with two quick applications of the formula we just worked out. One of which is something that you may a lot of people have just observed. If you add up an entire row of Pascal's triangle, let's see the row sums. The first row is 1, the second row is 2, 1 plus 2 plus 1, that's 4, and then I guess I should call this the 0th row, the first row, that's the second row. Anyway, the sum here is 3 and 3 and 1 and 1, that's 8. 1 and 4, 10, 11, 15, 16? Mm-hmm. Oh, are you able to guess the pattern here? So that's something you can state as a theorem. Let me try to fit it up in the corner. The sum of n choose k, where k runs as throughout the whole range that it can, from 0 to n, is equal to 2 to a power. What power is it? It's the same as the row we're in, which is the upper limit of this sum, so it's 2 to the n power. And how do we see that that's true? Well, I mean, we just observed it, but calculate 1 plus 1 to the n with the binomial theorem. So basically what I'm saying is set x equal to 1 and set y equal to 1 in the binomial theorem. Both x and y are 1s, then the part of the binomial theorem that has powers on x and y, it just becomes ones. So it immediately falls into this. This has slightly the feel of hitting an ant with a sledgehammer. I don't think that's the right saying. You know, using a really powerful tool just to prove something that's fairly simple. The other way to see this fact is that the total number of subsets of a set is 2 to the n. Why is that? Well, if you're building a subset, for every element, you've got a binary choice. Do you include it in the subset or not? So you have, for each element, 2 possibilities. That's 2 raised to the n power. The other way of thinking about it is you can organize the sets based on how big they are. So there's the unique empty set, then there's the sets that have 1 thing in them, and the sets that have 2 things in them, and eventually the sets that have n things in them. So you're just using the addition principle, because those are disjoint cases, right? The 2 sets that have different sizes are not going to be mistaken for one another. Okay, so again, fly sledgehammer, but there's another result that's not quite as easy, but it's easy enough in certain cases. Let me look at the even rows. If instead of just adding, I put a -1 to the n kind of into it. I just treat that one as plus, this one as minus, that one is plus, this one is minus. Do you see what you're going to get? Well, the ones, one of them's plus and one of them's minus. The 3, one of them's plus and one of them's minus. This is 0. It's an alternating sum. That's what that's known as. I don't know what to do with, well, I guess the alternating sum is 1 in the first case, even if you do that. But after the first case, this one would be 1 and that one would be minus, so 0. Now this is weird. In the middle here, it's well, this is an odd length row, right? It's 2 choose n or 2 choose k, but because 2 is even, there's an odd number of possibilities. 0 through 2, right? So we get a +1, a -2, and a +1. I don't have this sort of, the one on the ends cancel and the ones in the middle cancel each other. There's nothing like that. These are both 1s, but overall it still cancels. You get 0. Check that saying out, the alternating sum for row 4. 1 minus, plus, minus, plus. Fine. Flip the signs as I go through there and add, I get -3, +3, -1, 0. So why do you think the alternating sum always comes up 0 after we get past that initial one where there's a single term in it? Okay, row 5 is the easy type where they cancel from the ends. But row 6, 1, -6, +15, -20, +15, -6, +1. If you add up all the negative terms, you get 20 and 6 and 6, that's -32. And if you add up all the positive terms, 15 and 15 is 30, and 1 and 1, 32 also. So again, zeros. So why do you think, how can we prove that using the triangle, using the binomial theorem? I'll give you a hint. It's the same trick, except we're not going to have y be 1. What value of y will give us this result? Maybe you'll see it. In case you didn't see it, I went too fast, but we'll have 0 to the power, so of course that'll give us 0. And if y is -1, okay, but why is y equals -1 the right thing to do? That's exactly what you want to do to get this alternation. Okay? In the binomial theorem, you have n choose k, n choose k, x to some power, minus k, y to some power, k. So if y is -1, you're going to get a flip back and forth. The x being 1 means this term might as well not be here. But the y to the -1 to the k is what causes the alternation. So judicious choices of what plugging x and y values in can give you results right out of the binomial theorem. And I think that is probably a good place to stop.